Okay, this is the video for the Law of Large Numbers lab, and this lab is going to be somewhat simpler than the last lab was. That first lab on randomness, I really threw a doozy at you. There was a lot going on in that spreadsheet. In this lab, there's going to be a lot less going on, and what I've chosen to do is to go ahead and produce the lab. This is the spreadsheet that you're expected to make, and I'm going to give you some tidbits on how to calculate various things. There's going to be one step, or maybe 1.5 steps, that I'll leave to you. Okay, the first thing I'm going to notice is over here. I've got two columns that extend down beyond the page. The first column has a bunch of random numbers. These are random numbers chosen between 0 and 1. To get a random number between 0 and 1, you type, I'll do that right here, equals rand, and there's nothing in the parentheses. Okay, press enter. That gives you a random number between 0 and 1. So what you want to do is to generate 10,000 of those, and that's what I've done here. If I hold down page down, that goes down pretty fastly, but if I get impatient and I want to just go to the bottom, I can press Control down and see at the very bottom of the spreadsheet that row 10,000, and then press Control up to go back up. So you'll want to create these 10,000 random numbers, and then we're going to use the convention that there's a 51% chance that a newborn is a female and a 49% chance that it's a male. So to create random genders, we're going to take a random number, and if that random decimal number between 0 and 1 is less than 0.51, that's going to represent a female, as these first 5 numbers are. If the number is greater than 0.51 or equal to 0.51, we'll have a male, and it's an extremely low probability that you'll have equal to 0.51. So the or equal to doesn't really matter much. So you're going to use an if statement to change those random numbers into males and females, denoted by F's and M's. Okay, and now let me delete that random number that I had. I do want you to keep the spreadsheet so that those are equal rand formulas. I don't want you to copy just these values. I want you to keep it with the formula so that those can be recalculated, and I can test how well your spreadsheet works when you submit it. Over here, I'm looking at different sample sizes. So let me choose this first row, for example. For n equals 5, I'm taking the 1, 2, 3, 4, 5. Those first 5 genders, and I'm looking at them. And right next to it, I calculate the relative frequency. That's what's meant by RF. And the relative frequency is the number of females divided by the number of genders. Here we have 2 females divided by 5 genders, so 2 divided by 5 gives us 0.4. And it turns out that there's quite a lot of males here, so even if I go down to the 10th gender, I've got 2 of those 10 genders are females, so the relative frequency of females is 0.2. Okay. If I were to go down to 100, I won't do that here because it would take a long time to count, we would find that 0.44 is the ratio of females to total genders. So that would mean that there's 44 females out of the first 100, and then the first 1,000 there's 491, and the first 10,000 there's 5,150, or excuse me, 5,115 females. Okay. Now what I am going to do is show you how to calculate these, and to do that I'm just going to delete what I have there and we'll reconstruct it. And I know these keep recalculating, but don't worry about that. It's not a problem, just focus on the formulas that we're doing. Okay, so for this first one, I want to, first of all, count how many of these first 5 are female, and then divide by 5 to get the relative frequencies of females. So I'll use a count-if statement that we used a few times in the last lab. And let's see, I want to count between H1 and H5. So I'll have H1 colon H5. That's my range. And then the criteria is female. I'll just use a capital F, put it in the quotations because it is text. Close off that parenthesis, and if I just press enter, that counts how many females there are. Okay, if I do it again, then I get 3. We don't want how many females there are, though. We want the relative frequency, which means I take this number and I divide by how many there are. Okay. So what I'm going to do is just simply enter divide by 5. And that gives me the decimal version of the relative frequency of females to total genders. Okay. Okay, now, you could go ahead and type those individually for these 5 different sample sizes, but what I'm going to do is fill down, and that's because I really want to study how these spreadsheets work and how we can work with them without having to tediously go through and modify every single little cell or formula. Now, when I filled down, I forgot to tell you what I was doing. I highlighted cells B3 through B7, and I pressed Control D for down. What that did is it took the formula in cell B3 and it copied it to these other cells, B4, B5, B6, and B7. Now, it didn't copy it exactly. Notice the formula up here. That's in B3. Now, if I switch to B4, what happened? These two numbers changed. B3, B4. So first thing I notice is that both of the numbers changed. In this cell, I want to be calculating the relative frequency for the first 10 genders, so I don't want to start at cell H2. I want to start at cell H1. In other words, when I fill this down, I do not want this 1 to change. And the way I can signify that is go back to B3, enter in a $sign, and a $sign in a formula means that what comes after that $sign is not going to change when the formula gets filled down, filled to the right, or copied somewhere, copied and pasted. Okay, I'll press enter, and then if I fill down, you'll notice that first value stays H1. Okay, and the $sign is still there, but it's referring to H1. The $sign tells it not to move it when we fill down. Now, if I'm looking at the first 10, I don't want to have H6. I instead want to have H10. And then I want to divide by 10. Okay, so that looks at the first 10 genders, counts how many of them are females, and then divides by 10. I press enter, and that gives me the relative frequency for sample size 10. Change this to 100, change the 5 to 100, press enter, change this to 1,000. There is a way to link this number to another cell, but it's actually pretty complicated, and I'm not going to do that in this course. How to have a cell reference, the actual row of a cell reference, be referenced from another cell. For our purposes, we won't need to. Okay, so I'm just going to go through and change those by hand, and I could have changed the H1s by hand. It's not a problem if you do that in your submission. I just wanted to show you the $signs because it's a good opportunity. That's a very powerful tool. Okay, and what we see here is the law of large numbers in action. And the law of large numbers tells me that if I have a lot of trials, like 1,000 or 10,000, then the relative frequency will tend to be close to the probability. In this case, the probability was 0.51. That's how we set the simulation up. Notice that in my small sample sizes, I was not too close to 0.51. I was in the right ballpark, but certainly a little ways away. Now, what happens if I recalculate? Well, I can find that out just by, click on a cell and enter in a 0 and press enter. I see the same kind of thing happening. For the small sample sizes, our relative frequency really isn't that close to 0.51. As we increase sample size, however, the relative frequency does get close to 0.51. One thing to notice here is that increasing sample size doesn't always make the relative frequency closer. This is an example that, in particular, at 1,000 trials, we had a relative frequency exactly equal to the probability. But when we went to 10,000 trials, that relative frequency had deviated a little bit from the probability. So we can't always say that increasing sample size will give us a more accurate estimate of the probability. Instead, increasing sample size makes it more likely that we get an accurate estimate of the actual probability by the relative frequency. See, if I calculate it again, that 1,000 trials was further off. And if I calculate it again, we see that the variation is bigger for the larger sample size. I mean, we've seen 0.2, we've seen 0.8 for sample size of 0.5. sample size of n equals 5, but down if we have 10,000 numbers, that really doesn't deviate far from the actual probability of 0.51. Okay, so this spreadsheet shows the law of large numbers in action, and just email it to me, and that will be your submission for Lab 2.